Welcome to the second exercise video on my channel A Woman in Physics. Last time we did a simple exercise on the kinematics of point masses, and this time we are still staying in this general field of kinematics of point masses, but we will add in addition considerations about the energy of an object. And without further ado, let's start. From a 30-meter high tower, a stone is thrown with a speed of v0 equals 72 kilometers per hour at an angle of alpha equals 30 degrees with respect to the horizontal. A, at what speed, B, at what distance from the tower, and C, after what time does it hit the ground if the air resistance is neglected. So, what do we take out of this? We have a couple of given values. First of all, the height is given with h equals 30 meters. Secondly, the initial velocity is 72 kilometers per hour. Now, this unit, kilometers per hour, is not the basic unit. And in order to make it simple for ourselves, to not think about converting units later during the calculation, we can do it right here. And 72 kilometers per hour equals 20 meters per second. And finally, the angle alpha equals 30 degrees is given. So on the other hand, we have also three variables that we are searching for. On one hand, we are searching for the final velocity, let's call it v1. Then we have the distance s from the tower and the time t where the stone hits the ground. So let's make a short scheme of what's happening. So we can put our landscape into this diagram. On the horizontal axis, the x-axis, we have the distance from the tower. The vertical axis is the height above ground. And we can see that there is a curve representing how our stone moves through the air, and we have an initial height of 30 meters and a certain angle. But how do we calculate now our three values we are searching for in detail? Well, first of all, let's have a look at the law of energy conservation. What does it tell us? Basically, the total energy of the system does not change. So we have an initial state where the energy of the state is the sum of the kinetic energy, which is the energy of motion, and the potential energy, which is the energy of the location above ground. Then we have the final state, and in the final state we've been hitting the ground. And if we think about putting the ground, which is y equals 0 in our scheme, basically as some level of reference, then we do not have a potential energy here, but rather the potential energy of the initial state takes the height difference into account. Energy conservation means that the total energy is constant, so the energy of the initial state equals the energy of the final state. And we can simply set them as equal and put the equations, the respective equations, into the equation. And what we get is this equation where the kinetic energies are, in each case, on the left-hand side, the first term, and the only term on the right-hand side, mass m divided by 2, multiplied with the respective velocities squared. Of course, in the initial state, we have velocity v0, in the final state, velocity v1. And on the left-hand side, we have a second term, the one that describes the potential energy, which is the mass m multiplied by g and h. Now, h was the height above ground, and g is the gravitational constant. And apart from the fact that the gravitational constant, if we measure it, depends actually on the location on Earth, it can be assumed for calculational purposes that g is constant, and there has been an agreement that g is used in such calculations as 9.81 meters per second squared. So we can take this as given. And what we see is that the mass m is a factor in all three terms. So we can divide the whole equation by mass m, and what we get is a simplified equation where we see that it doesn't matter how heavy or light our stone is. And when we have one final last close look, we realize that there is only one unknown variable in this equation, which is indeed the final velocity that we are looking for, v1. And what is it? Well, if we put it around and transform the equation so that v1 is on the left-hand side, we can see that the final velocity equals square root of initial velocity squared plus 2 times gravitational constant and height h. So we can take our parameters, put them into this equation, and we can do it with a calm conscience because we know that we've transformed all units into their base units, and we can calculate that the final velocity equals 31.4 meters per second. Or, since all our initial variables were given as natural numbers, we can say that final velocity equals approximately 31 meters per second. So this is one thing that we were actually looking for. But since we're talking here about velocities, let's have an additional look at the equations of motion. And what we know is that when we follow our horizontal axis, we know that we have a uniform motion along the horizontal axis because there are no forces along the horizontal axis. So our object is moving in a uniform motion. And we know that for any uniform motion, the distance x equals velocity in that direction, which is in our case the initial velocity v0x multiplied by the time t. On the other hand, in vertical direction, we have an evenly accelerated motion because we have the gravitational force. And you can see that this is the general equation of an evenly accelerated motion, where we have the vertical direction y, which starts at y equals 0 and has a direction from the ground upwards. And therefore the acceleration is not g, but minus g, because the gravitational force always points downwards. So the equation is y equals minus g half multiplied by t squared plus velocity in vertical direction, the initial velocity in that direction, v0y multiplied by t, and plus the initial height h. So what we don't know is what are the initial velocities in x and y direction. And to answer this, we can make a simple scheme. Our velocity is basically a vector that has a certain direction under a certain angle with respect to the horizontal. And you can see here that you have basically a triangle where your vector v0 can be split up in a horizontal and a vertical component. And adding up these two components yields our result of v0. And in order to calculate it, we can use easy mathematics. And it's done in such a way that the velocity with respect to the horizontal direction, v0x, equals v0 times the cosine of alpha, whereas in vertical direction we have to take the sine of alpha into account. And we can use this in our equations of motion and substitute simply v0x and v0y. So does this help us? Yes, of course, because v0 and alpha were given. And when we have a closer look, we see that, well, not all of the variables that we can see here are given. Basically, the question is, what are x and y now in our consideration. How can we explain what x, y, and t are? And of course, t is simply the time when we throw the stone, and we can think of it as a parameter. And we can calculate x as a function of t and y as a function of t. But of course, we can also plot y as a function of x. And this is precisely what we've seen before in the scheme. And it's shown here again. And you can see here on the right-hand side, this was actually what has been shown before in the scheme. But in addition, when we think of t just as a random variable, we could make it smaller than 0, and we see that then we get this full function, which has basically these two branches. But we are not interested in the two branches, we are only interested in everything x larger than 0, which is t larger than 0. And the question is now, we were searching secondly for the distance s. For that, we can combine the two equations of motion and eliminate t. And this can be done in a rather simple way. We take the first equation, x equals v0 times cosine alpha times t, and we write it such that t equals x divided by v0 and also divided by cosine of alpha. And we can put it in the second equation, and what we get is shown here, which looks rather complex. And we see that we still have x and y in this equation. And what are x and y in detail? Well, basically, we've seen it before. It's every location during the motion. But we are looking for a particular one. We are searching for the distance s. And the distance s is measured along the horizontal direction. So we are looking for the point where x equals s. And this is exactly the point where y equals 0, where we hit the ground. So we can take our complex equation of motion and substitute x by s and y by 0. And now we are nearly done, because when we have a closer look, we see that the parameters on the right-hand side, g, v0, alpha, and h, are given. And s is the only unknown variable, and it's the variable we are searching for. So we have basically solved our problem. Well, nearly solved our problem. The only thing that's left to do is solving a quadratic equation, which has a form of 0 equals s squared plus ps plus q. And we can solve this rather easily. We know that there will be two solutions, s1 and s2, and it comes from this mathematical construct that the solution of any equation that's given like this, where the solution then is s1 and 2 equals minus pi over 2 plus minus the square root of pi squared divided by 4 minus q. And we can then simply put all our given values in their basic units again into this solution, and what we get is that S1 equals 64.0 meters, which is 64 meters, and on the other hand S2 equals minus 28.7 meters, which is approximately minus 29 meters. Well, we know that this negative solution is in our context unphysical, since we are throwing the stone forward, but we've seen this solution in this left part of the extended scheme right here. But as I mentioned before, we are throwing our stone forward, so we can neglect the second value. And if we think about it, yes, we've calculated the final velocity. Now we've calculated the distance at which our stone hits the ground. So what's left to do? We need to calculate the time t. And this is rather easy, because we know, according to the equations of motion, there's a horizontal motion where the distance x equals, in our case, s, where we hit the ground, and this is precisely equal v0 cosine alpha multiplied with t. And if we put v0 and cosine alpha on the other side of the equation, we can simply calculate the time. And the time t equals 3.7 seconds, which is, if we take again only natural numbers, 4 seconds. And I would like to mention here that if you're using this as preparation for your exam, then you should take into consideration, yes, I'm a huge fan of comparing the results with the values that are given. And usually if I give my values in natural numbers, I like the result to be in natural numbers as long as it makes sense. On the other hand, as I said, if you're using this for preparation for a final exam, please take the opinion of your teacher or professor into consideration. And with this, let's have a final look. Yes, we've calculated the final velocity v1, we've calculated the distance and the time where our stone hits the ground. So everything we were searching for has been calculated, and with this we are done with today's task. So I would like to thank you for watching, and I hope you didn't have any problems, but if you did, let me know, and if you liked it, please also let me know in the comments below, and I hope to see you soon for the next video. Bye!